So, hello, welcome. My name is Professor Bob Bear, and I'll be teaching you for this term. And I'm also a module leader for Math 2005 Modelling Theory and Practice. And I just want to take you through these introductory slides this morning. So it'll be quite sort of backgroundy, sort of trying to get a motivation for the topic. It's always very good, as you can understand, to have a motivation. Well, why bother with this module right at the beginning? So we can, when you get sort of stuck in the harder maths, it's all worth it. So hopefully by the end of these next two videos, you'll have a clear idea about that. And so the first question I'm just asking is, what are numerical methods? So you come across these last year with John Thuban's module, Math 1003. And here's my sort of take on that. Is basically you've got two boxes. You have your continuous equations, which are all the maths you've maybe done by hand in the past, ordinary differential equations, matrix problems, root finding, so on and so forth. But you want to solve them on a computer for whatever reason, maybe quite often because it's too difficult or maybe impossible to solve by hand. So what we do is then we translate these continuous equations, whether they be differential equations and so on and so forth, into a set of algebraic equations. So we actually simplify in some ways this set of equations. We allow the computer to do it. And what the computer does very well is iterate. It goes over and over again, a series of tasks. And that's the key concept in numerical methods, is what is the iteration we're using in this process. So that's just a little emblem to keep at the back of your mind as we go forward with this stuff. And the applications of numerics and optimization are huge, and this is just a sample of some of them. The first one, which is very close to applied mathematics, is fluid flows. And let me just write a couple words down on the board to give you an idea of why that's important. So for fluid flows, the governing equations, and you don't need to know what they are, but let's just write the words down. They're called the Navier-Stokes equations. Okay, and the key point about these is they have quadratic nonlinearity. So quite often you'll have terms in the Navier-Stokes equations which look like this. So let's just do it in partial derivatives. So you have partial u by dt. Again, you don't need to know this in detail, but you have terms that will maybe go like u du dx equals something. And there's your quadratic. So your u is your thing you're solving for, and that's your quadratic nonlinearity. Okay. So this is what makes them so hard to solve, but they're also fluid flows come up in so many real world applications. So if we just go back to the slides now. I've just mentioned a few. Formula One cars. Okay, so if you want to predict the flow of a Formula One car and you wanted to make, essentially you want to make it smooth as possible, to make it car goes fast as possible, then you need to solve these fluid equations. Another example is weather and climate. This is my research area, in fact. If you do my fourth year module, you'll learn more about this modelling for weather and climate. And basically you've got the globe and you're trying to divide it up into little boxes and then model the fluid equations in each of those boxes. And finally we have modelling of other planets, which is basically translating that same weather and climate problem on Earth to other planets. So that's a bunch of fluids. There's other ones you can think of. It's almost as restricted as your imagination in some ways. Another sort of so that's a sort of a differential equations type application, and that will relate to part 2 of this module. And then there's something that relates a bit more to the matrix problems, the section 3 of this module. I'll get onto the summary of the module in a minute. And that's Google. So believe it or not, Google, when you do your search engine and you rank whatever you're searching for, say it's coffee, what a common search I imagine, it will rank them in order. And I wonder if you ever wondered how it does that. Well, it turns out that actually underlying that there's this thing. There's an eigenvalue problem. So you're right, you've done eigenvalue problems in 2x2, but this is an eigenvalue problem of a really big matrix. The Google matrix contains all the information that for searches, and you're trying to find the eigenvalues, and quite often you're just not trying to find all the eigenvalues of this huge matrix. You're trying to find the leading values, and so the largest one and the next largest one. And turns out there's a method that we're going to study called the power method that iterates to find this eigenvalue. So we'll do that in part 3 of the module. But so there's this algorithm called PageRank, which part of it's named after Page, who was one of the founders of Google. And it's central is this power method. There's other maths there as well, graph theory, other stuff. But that's what we say. The one little bit of this magical Google search engine that we use uses this power method, which we'll cover in matrices. A third one is financial modeling. This is an example of equations, the Black-Scholes equations. Now, quite often this has been offered up as a group project at the end of term 2 for this module, and it involves solving equations with numerical computation, but it often has a stochastic element in there. So you have your sort of deterministic bit of the equation and your stochastic bit, and that is a very common method in applied maths for modelling a huge variety of problems, whether it be the financial markets or pollution modelling. So they're just 3, and there's many more. And I just hope it gives you a flavour of why it's such a fun and important subject. Now, there are 2 sides to what this term. The first 3 parts of this term we'll call numerics. The second bit is probably a new idea to you. It's called optimization. All optimization means is performing a minimization or maximization of a big function of multiple variables. And it turns out, whilst that sounds on the surface to be quite a sort of slightly dull topic, it turns out there's a huge number of really useful the problems rather can be posed as a minimization of a big function of multiple variables. And here's examples of 4 of them. First one is a traveling salesman problem. We don't cover this in this module, but it's kind of a classic problem in computer science. And it says, if you've got a list of cities and distances between each pair of city, what is the shortest possible route that visits each city exactly once? So it's like a sort of really a model route finding problem, and returns to the original city. And that's sort of an example of an optimization problem. You're trying to find out of all the multiple options of route, you find the one that minimizes the distance whilst visiting each city once. Finding the optimal distribution of components on a circuit board, very important for our phones, for example, that they have produce as little heat and are as small as possible. Bigger problem is starting a numerical weather forecast. Now, so when you start a weather prediction forecast at the Met Office, down the road, we need to combine 2 main sources of information. We need to find what are called observations, which are things like satellites and weather balloons and temperature sensors on the ground, etc., etc. This huge sort of vat of data sort of comes in to the Met Office. And then you've got the state of your model that you're simulating the weather with. And somehow you need to combine all that information to find a starting point, an initial condition for your weather forecast model. So it turns out that getting these initial conditions is about minimizing a cost function. So you have a big function of multiple variables, and you minimize that with respect to those variables. And the method they use to find that will be very similar. Certainly similar in its basic nature to the one we'll study at the end of this term. So that's optimization. And another final example is find an ideal spacecraft trajectory, out of all the possible ones. So optimization turns out to be incredibly central to a lot of problem solving. So this module has 4 parts, as I've sort of alluded to before. Let's go through what those are. So part 1 is root finding, part 2 ordinary differential equations, part 3 matrices, and part 4 optimization. Now parts 1 and 2 are deliberately designed to be the ones that you've encountered before in some guys. So don't be surprised if we come across bisection method or fixed point method, but hopefully you'll see that we'll go into in more depth. We'll analyze it a little bit more closely the conditions for convergence, and this is quite a short section, but it's important. It sort of sets up the theme for the rest of the module. And then we go to ordinary differential equations, some of which methods you would have studied, some methods you may have used but you may not have understood in that much detail. So hopefully at the end of this, again, there'll be a bit of overlap last year, and we'll take it forward. Now this module used to run on its own in the second year, and then 2 years ago Math 1003 came along, and we've had quite a bit of discussions with the module leaders and also the students who've taken it over the last 2 years, whether this overlap is an issue. On balance, it's mostly people quite like the refresher at the beginning of term on familiar grounds and the sort of confidence building that comes with it. So we've kept it like that, and we hope that makes it enjoyable. We're conscious of these overlaps, don't get me wrong, but we think it actually might be beneficial to sort of reinforce things, because by the time you get to certainly matrices and optimization and the material of term 2, it's all completely new. Finally, I just want to talk about how we're going to structure this. The structure is the same as last year, but much more digital content. So obviously I'm giving digital content here in place of the lectures, the physical lectures. And practicals we can actually be in computer labs probably, where maybe we're assuming we can't. So what we're going to do in the place of that is a few more resources. So for the practicals, I'm going to bring in these sort of these live scripts. So for the practicals, we've got these MATLAB live scripts. And the idea of live scripts is they combine theory and code. And you can run the code, because it's a MATLAB component, you can run the code within it. So it brings it all together. And one challenge sometimes for mathematicians with this topic is sometimes people whiz away with the theory, but they can't make the link to the code. But if you ever use this out in a company or something, you're going to want to do the latter as well. So I've introduced these sort of these live script resources this year, sort of a new feature in addition to my videos, to try and aid that, and I would really advise having a look at it individually with your MATLAB resource before any live sessions we have to discuss it. So in a sense, you've got that there, and you can work through it. And what I hope to do is sort of give it in a form that the code's there, but you can then play with the numbers and then see the link with, and try and go through the code and find a link with the theory, much as we would have done in physical practicals last year. So we're doing our best to provide some sort of correspondence between the experience last year and experience this year. I hope it's an enjoyable experience. So we have 5 of these practicals that run on even weeks, 2, 4, 6, 8 and 10. So 5 of them. The first one will be kind of a MATLAB basics thing, getting your feet under the table again with MATLAB if you build confidence. And then each of the 4, 6, 8 and 10 will be correspond to each of the topics, the root finding, ODEs, etc. And then alternating with that, we have tutorials which are basically past exam questions. And again, I'll give out the sheets for that, and we'll try and go through those in any live sessions. So these all support the one coursework of the term, which is 20% of the mark, which is just handed in the end of term 1, and I'll try and set as early as possible in the term, so you've got plenty of time to work on it and plenty of time to get feedback from me on it, which will typically cover more of the first half, of term, maybe a little bit on optimization, but we sort of defer some of the assessment of that latter bit of term 1 to term 2, as you can understand. Okay, so it's sort of a reasonably long kind of report-based bit of coursework, but supported by all these practicals and tutorials. Okay, and what I do is we don't do the practicals in term 2. We sort of allow you to be a bit more independent. So do take advantage of the practical input in term 1. Okay. And then we move on to how we learn about numerical methods, which will be the topic of the next video. I'm trying to keep these videos under 20 minutes for for your attention, and also to try and keep me as fresh as possible. So the way I see it is that for each what would have been an old style lecture, we're going to have 2 videos, because there's a lot of faffing around in normal lectures and pausing and stuff, whereas it's a continuum with the videos. So this is how we're going to sort of provide equivalent content this year and get through the material. So I am working through my lecture notes. I didn't mention that at the beginning, but they are your sort of real go-to resource for this module. Let me just show you what they look like at the front. Okay, they're on LE modelling, theory and practice, some sort of picture of a keyboard, and an ODE translating. And I put these together 3 years ago. I translated all the sort of handwritten notes, which I've inherited from previous lecturers and I've done myself, and I put it into a sort of LaTeX document. So it's clearer. It has less bugs, I think, and it's easier to remove bugs. So if you see any sign errors or typos or stuff, do tell me, and I'll update those notes as we go forward. But hopefully that's a very helpful resource. And I don't try and give it out in dribs and drabs. I just give the whole, basically what will take you to the middle of next term material. So it's just over 100 pages, I think. And you can look ahead. So if you are finding it dragging because you're very familiar with some material, you can always jump ahead, and I assure you probably it will be new to you then. So use that as a resource as well. There's quite a bit of time gone into that, Okay, so I'm going to stop this video now just before 20 minutes, and I'll see you at the next one where we carry on this introduction to Math 2005. Okay, bye now.